Hi all, welcome to the Granth. In this video, we are going to learn about another searching mechanism in graph or another way to traverse a graph, and we call it depth first search. So let's look at the index and we'll come to know what all things we are going to learn in this particular video. First thing we'll learn is an introduction to DFS, like what is DFS, how it works, the complexity, all those things. We'll learn about the explanation of the algorithm, uses, and finally we'll see the code for DFS. So we'll cover all these as part of the video. You can jump front and back in the video as you like. If you are familiar with introduction, jump directly into the code. Or if you want to know the explanation of the algorithm, just have patience and scroll through the video. So let's look at the introduction to depth first search. So it is an algorithm to search a node in graph. It is similar to like BFS. It's another algorithm. In BFS we go breadth wise, which means that level by level. In DFS we go to the depth, and I'll come to the explanation in just in a while. What I mean by going till the depth. Runtime complexity of this algorithm is again O of B plus E. Space is O of V, but the space complexity of DFS is little better than BFS because when we talk about the leaf nodes, so in case of BFS, if there are multiple leaf node, we have to store a lot of the leaf node in our memory. Whereas in case of DFS, it will be little less. For example, let me draw something here. So if we have something like this, so it is a directed graph. You can think of it as a tree, and we have something here. Even this has something here, and this has something here. So if we do BFS, first we process this level, then we process this level where we are storing two nodes or two vertices, and finally we come here where we store four vertices. And if I go down, then number of vertices will increase. And suppose if this is like a tree, but rather than this, if we have something like this where we have more vertices at the leaf node, so number of vertices that we are going to store will be more. So it will be everything which is at this particular level. In case of DFS, since we go depth wise, so we will store, the processing will be this way. So we'll go from here, then to here, then to here, and then we trace back to this vertices and come back here. So at max we are storing only these three vertices. So in this example, either these three, or we will store these three, or we will store say these three. So that way if we see, storage wise it is little less. So space complexity wise both DFS and BFS are similar, but like I showed you with the example, DFS is little more space efficient as compared to BFS. It is sort of greedy algorithm because we go as long as we can go to the depth. So that is why it is used mainly in solving problems like a maze problem, where we have to find path, not the shortest path, the path. So let us see how DFS works. So I'll take an example of similar to what we had in BFS. So we have a node A here, then this is connected to node B, this is connected to node C, let's say. Then we have something like here D, let's say there is E and F. So if I have to do DFS, what I need to do is we'll use a stack data structure here, similar to in case of BFS we used a queue because we wanted to process layer by layer, so it was always first in first out. But in case of DFS, since I have to go long, or I have to go till the depth of the tree or the graph and then come back and basically backtrack and go back to another branch. For example, in this case I need to go from A to D, then D to F, and since there is N to F, I need to come back to D and then traverse back to E. So since I have to follow this approach, in this particular scenario we will not be using a queue, and we will be using a stack. Why we will be using a stack is because it is last in first out kind of data structure. So we will have a stack here. Please mind the handwriting. So let us say this stub is the stack, and we'll also use a set. So set is to keep track of which all node or which all vertices we have already visited. So let's say that we start from this vertex A. So what I'm going to do first is I'm going to add A to my stack, and also I'll add A to the set. So that in this case the diagram that I have drawn is a directed graph, but it can happen that it is an undirected graph. So just to keep a track of which all vertices we have visited, we have this set. So we have added these two. Now next what I need to do is I need to pop this out of the stack and check the neighbor or what are the adjacent of A. So in this case we see that adjacent of A is B and adjacent of A is D. So what we are going to do is, since we have popped A from the stack, so let me redraw the stack here. Since we have popped A, so the stack was empty, and in any order I can basically add B or D in my stack. So I will say that okay, first I added B and then I added D to my stack, and since A was popped, A is added to the set. Next what I need to do is let me remove the tick mark from B and D as well. So I don't need this, I don't need this. So next what I'm going to do, from my stack, I will traverse this stack as long as it is not empty. So I will pick up D, I will pop this out and I'll add it in my set. So I'll say that D is also visited. Since D is visited, next what I need to do is I need to visit the neighbor of D. So neighbor of D is E and F. So I need to pop D out of the stack. Let me pop D out of the stack. Let me remove this. And since next I need to visit the neighbor of D or visit the neighbor of of D, so I will add again here E and F. Again, it does not matter in which order I traverse. And since I have already visited D, I have added D in my set. Next what I need to do is, again I need to traverse the stack. I need to see or pop the topmost element. So I popped F and I add F in the set also. So this is the last element or last vertices in this depth. There is no child to F, so it means that I have traversed this path. So next time, since I have popped F out of this stack, so there is no child of F, so I'm not adding anything. So next traversal will be, I will pop whatever is remaining in the stack. So next element which is there in the stack is E. So I will pop E out of the stack, which is this element. So let us pop E out of the stack. I don't want this, I don't want this, I don't want this. So there is no child to E or there is no adjacent to E. So I'm not going again to add anything else in the stack. So what it means is that I have traversed till now. This path is traversed. I have traversed this path. Now the remaining element of the stack is B, which means that I need to traverse this particular path. So let us do that. So in this explanation, let me remove all these, and I'm taking very baby steps so that anyone who is new to graph, they won't have any difficulty in understanding. So the next element that I'm going to pop is B, and I will remove B from here. And sorry, I forgot one thing. Since I popped E that time, I need to add E to this stack, to this set, which means that E is already visited. So now I'm popping B out of the stack. So let us remove this. And since I have popped out B, I need to add B in my set. So in the end here, I'll say that I'll add B as well. Next, I need to see what is the adjacent of B. So adjacent of B is C. So I need to add C in the stack. And once again, we'll traverse this stack and we'll see what is the element remaining. Now C is the only one that is remaining. So I'll pop C and I will add C here in this stack, in this particular set, and I will remove C from my stack. Now C does not have any other adjacent vertex, so I'm not going to add anything there. And the stack, I will say that the stack is empty now. So since stack is empty, I will come out of this traversal of the graph traversal. So whatever is there in my set, this gives me the order in which the depth first search happened. So depth first search happened from A to D, D to F, then to E, then B and C. So this is how depth first search works. And in place of stack, we can use the operating system stack and use recursion. And I will use recursion in the code to show you how you can use or implement this particular feature. I hope the traversal logic was clear to you, how the traversal has happened and how depth first search can be implemented. So let's move to the uses of DFS. It can be used in finding shortest path algorithm like topological sorting. So not exactly the shortest path, but you can order it in a topological way and then find the shortest path based on certain criteria. So we'll look into that when we are going to solve some problem based on topological sort and DFS. Next is for web crawler. So if you have a site, you can have list of crawlers there, like list of website in a particular URL. You have list of URL, then you can take each URL and go as long as you can go. That is web crawler for you. Cycle detection of the graph, again BFS, DFS both can be used. DFS will be little space efficient. And so finally for solving maze problem. So after this video, the next video that I am going to make, I will use DFS to solve maze problem. I'll pick one problem from lead code and I will solve it for you. So these are the uses of DFS. Now finally we'll jump into the code and see how DFS can be implemented. Let us look at the code for the DFS. So it is very straightforward. We have a vertex here which contains name, visited and adjacent list, and we'll use recursion to solve to implement DFS. So let's look at the graph where the kind of the graph which we are using to implement DFS. So if we see, we have this vertex A connected to B, vertex A is connected to C, and both are connected to D, and that is what D is connected to E. So we need to run DFS on this. So what we did here is that the root vertex here, for example, I have taken as VA. So we'll start from A. So what we need to do, let me just scroll it a little this side. Okay, so first we set root vertex or the vertex A as true, which means that it is already visited, and then we'll look at the adjacent vertex of A. So we need to traverse B and C. So here, if you remember in the last example, I was using a stack. So in this case, since we are using recursion, so stack will be used from the operating system stack. We don't have to explicitly use a stack here. So here we'll say that if the adjacent vertex, so for example, in case of A, if we get first adjacent vertex as B, we'll see if it is visited or not. Since it is not visited, so we'll mark it as visited and then do a DFS from the adjacent vertex, which is from B. So this will recursively call the DFS, and the root vertex in that case will be B. So this is the simple implementation. I hope it is pretty clear. It's pretty straightforward and simple, like whatever I explained in the video. Let us run this and see how it works out. So it has printed A, B, which is this vertex, then it went to D, then it went till E. So this was the biggest depth. Then it traced back till A, and the remaining one was C, so it printed C here. It never printed D and E again because it was already visited. So this is a simple implementation of depth first search. So I hope it is pretty clear to you and how the recursive solution has worked. We can also implement it using an external stack rather than depending on operating system stack. So in that case, we don't need recursion. We can work with the stack like how I explained in the theory section. So that is it for this particular video. In the next video on DFS, we'll solve some problem based on DFS.